Many developed cities in the northwestern Pacific region are located along coastal areas, making them naturally exposed to typhoon hazard. And in the context of climate change, potential increase in tropical cyclone intensity or frequency may pose growing threats to the life safety, economic stability, and even social resilience to our living society.
Despite these increasing risks, existing studies on future typhoon hazards still focus on needed attention. Some areas worth of further investigations include: first, many publications talk about prediction of average typhoon wind speeds, with relatively limited published results on predicting future extreme typhoon speeds, which is actually the most direct factor affecting structural safety. Second, many predictions assume changes of typhoon intensity, the sole driving mechanism, with other important factors such as typhoon genesis and trick ignored. Third, notable verification are observed among published prediction results, leading to the concerns on uncertainty of these studies.
Summarizing what Duan and Tongfei just said, the objectives of our study are threefold: to establish a robust research framework with the above-mentioned limitations addressed, to quantify future changes in typhoon hazards in the northwestern Pacific region, and to reveal the physical mechanism driving these changes.
Improving confidence in projection results is a critical challenge, as some existing studies report a wide range of obstacles. These discrepancies may arise from differences in study methodologies or variations among the global circulation models, which are the projection based on.
To address uncertainties associated with climate models, this study adopts two key strategies. First, the analysis emphasized relative change between current and future climate conditions with the same TCM, thereby reducing the influence of the systematic biases inherent to individual climate models. Second, the final prediction results are divided from mean or multiple climate models, which helps minimize biases linked to any single TCM and improves the robustness of the overall predictions.
Uncertainties related to methodology choice is addressed through using a multi-approach study framework. Specifically, 3 independent approaches are employed. For example, in modeling typhoon genesis, one approach directly adopts identify typhoon center by detecting atmospheric vortices from global circulation model, and then fitting a statistical model, while a second approach derives statistical characteristics of typhoon genesis using a set model based on key marine and atmospheric parameters. The consistencies of findings among different approaches provide strong cross-validation. All 3 approaches indicate that climate change causes increasingly pronounced impact from lower to higher altitude. Traditional wind design practice is largely based on analyzing historical wind records, assuming that extreme wind statistics are stationary over time. As a result, reliance on historical data alone is becoming insufficient to ensure long-term design safety and reliability. The qualification of future typhoon hazard in Asian coastal cities in the current study can therefore provide valuable references for reviewing current structure wind design in the region to prevent erosion of wind design safety due to climate change.
In the context of Hong Kong, climate-informed future wind studies can provide several direct benefits. First, they offer a scientific basis for reviewing wind-related parameters in existing codes and standards. Second, they help raise public and professional awareness of the contingency or limitations of current wind design practices under a changing climate. Looking ahead, these studies can support a strategic transition from a minimum wind node-based design philosophy towards a future-oriented resilience-based approach to wind design. We look forward to seeing this happen soon.